Bismillahirrahmanirrahim. In this lecture, I am solving problem 5.70 from the book Fundamental of Thermodynamics by BORGNAKKE. So, the statement of the problem is a vertical cylinder fitted with a piston containing 5 kg. So, in the given data, mass is given to us is 5 kg of refrigerant. Working fluid here is refrigerant 410A and initial temperature is T1 is equal to 10 degrees centigrade as shown in figure 5.70. This is the given figure. Heat is transferred to the system, causing piston to rise until it reaches a set of stop. This is stop. The starting position or the original position of the piston is this. This is the original position of the, but after applying heat, the piston reach to this position. Here is stops. These are stops. The stops. It means that the piston cannot move beyond this point. The piston cannot move beyond this point. It means that at this point, after if we supply heat after this point, the volume will be constant. So initially temperature is constant because the piston move from this point to this point and volume being doubled. Volume is doubled and temperature is constant on the supply of heat. And then after this point, if we supply heat, the temperature increase to 50 degrees centigrade. So the statement is heat is transferred to the system, causing the piston to rise until it reach a set of stops. These are two stops, at which point the volume has doubled. Here the volume become double. It means that V2 is equal to 2V1. And here temperature is constant. T1 is equal to T2. From point 1 to point 2, temperature is constant. Additional heat. Now we further supply heat. Additional heat is transferred until the temperature inside reaches 50 degrees. Now temperature increases from T2 to T3 and new temperature is 50 degrees centigrade. When the piston is at this position and we further supply heat, then the temperature increases, at which point the pressure inside the cylinder is 1.4 megapascal, and due to additional heat P3 is equal to 1.4 megapascal. And as we know that 1 megapascal is 1000 kilopascal. So P3 in kilopascal is equal to 1400 kilopascal. And number A, what is the quality at the initial state? It means that required number 1 quality of steam. It means that find X1. And number 2, calculate the heat transfer for the overall process. Overall process means find the heat transfer from 1 to 3. There are two processes, from 1 to 2 and from 2 to 3. So first I explain the statement with the help of TV diagram. This is temperature in degree centigrade. This is volume in cubic meter per kilogram. This is the saturation curve. Initially temperature is 10 degrees centigrade. So let's suppose this is constant temperature line, and it is clear from the statement the initially temperature is constant, and we know that if we supply heat, there is supply of heat. If we supply heat and the temperature is constant, so this is possible in the mixed region. here. So it means that the initial point is here, something here, from 1. And point 2 may be here, this may be point 2 or this may be point 2, because from 1 to 2 temperature is constant, which is 10 degrees centigrade. Now additional heat increases the temperature to 50 degrees centigrade. It means that now let's suppose this is 10 degrees centigrade temperature, so the next increase in temperature is superheating temperature, because saturated temperature is 10 degrees centigrade and volume is constant. And volume is so this, it will be something like this, from 2 to 3. So point 2 is not clear. Point 2 may be this point. It means that we can draw this like this. So point 2 is not confirmed. Maybe this point or maybe this point. But from 1 to 2, it is clear that from 1 to 2 temperature is constant, and from 2 to 3 volume is constant. So process 1 to 2 is constant temperature process, and process 2 to 3 is constant volume process, and this is clear from the statement of the problem. Now we start solution. So in solution, first we will have to find x1, and then we will find heat from 1 to 3 for the whole process, for two processes from 1 to 3 we have to find the heat transfer from 1 to 3. So for x1, first we will find V3, because from V3 we can find V1, as V2 is equal to 2V1 and V2 is equal to V3. Second process is constant pressure process. If we find V3, so it means that V3 is equal to V2, and from this relation we can find V1. So we can easily find V3, and then with the help of V3 we will find V1, and from V1 we will find x1. So for x1 first we will find V3, then with the help of V3 we will find V1, and from V1 we will find x1. So we know that point 3 is in the superheated region, as it is clear from the statement that T3 is equal to 50 degrees centigrade is superheated temperature. So from superheated steam table, at temperature is equal to 50 degrees centigrade, T3 is 50, and P3 is equal to 1400 kilopascal. We can find V3 and U3. So if we check the superheated steam table here, so 1400 kilopascal, this is superheated steam table for refrigerant 410A, and this is the pressure 1400 kilopascal. 1400 kilopascal is available, but 50 degrees centigrade is not available, so we will do interpolation per temperature. So at pressure P3 is equal to 1400 kilopascal, temperature and degree centigrade, 40 degree centigrade and 60 are available, but we have to find V3 and U3 at 50 degree centigrade. So we will do interpolation for this. So in front of 40 degrees centigrade, in front of 40 and below 1400 kilopascal, 0.0 volume is 0.02127. Volume is 0.02127, and in front of 60 degrees centigrade, volume is 0.02371. 0.02371, and here we have to find V3. Similarly, in front of 40 degrees centigrade and below 1400 kilopascal, U1 is 270, internal energy is 278.93, 278.93, and in front of 60 the internal energy is 296.88 kilojoule per kg, and we have to find here U3. So by interpolation, first we are doing interpolation for T and V. So 60 minus 40, third value minus first value, divided by third value minus second value, is equal to third value 0.02337. This is 0.02371. 0.02371 minus first value is 0.02127, divided by third value minus second value. Similarly, do interpolation for this, for internal energy. So 60 minus 40, third value minus first, divided by third value minus second value, is equal to third value 296.88 minus first value 278.93, divided by 296.88 minus U3. So find V3 from this value. So if we calculate U3, V3, so V3 is equal to 0.02249, 0.02249 meter cube per kg, and U3 is equal to simplify this value and find U3, which is equal to 287.905 kilojoule per kg. Kilojoule per kg. Similarly, now as we know that V3 is equal to V2, second process is constant volume process, and V2 is equal to 2V1, double of volume V1. So this implies that from this equation we can write that V1 is equal to V3 divided by 2, which is equal to 0.02249 meter cube per kg divided by 2. So V1 is equal to 0.02249 divided by 2 is equal to 0.011245 cubic meter per kg. This is V1. Now with the help of V1 we can find X1. So as we know that form 1 is in the saturated region or in the wet region. So from saturated steam table, at temperature is equal to, from saturated table of R4110A, at temperature is equal to 10 degrees centigrade. Find VF and VG. Similarly, find UF and UG, because we will use these value later. So VF is equal to at 10 degree centigrade, this is temperature 10 degree centigrade, and in front of 10 degree centigrade, this is UF. UF is 0.000886. 0.000886 meter cube per kg, and Vg is equal to 0.022 0.02383 0.02383 meter cube per kg, and UF is equal to, this is the value of UF, 72.24 72.24 kilojoule per kg, and Ug is equal to, this is the value of Ug in front of 10 degree centigrade, 255.90 255.90 kilojoule per kg. Similarly, we can find P1 because P1 is saturation pressure, which is equal to, this is P1 1085.7 1085.7 kilopascal. Now we are finding x1. Now as we know that V1 is equal to Vf plus x1 into Vg minus Vf. So rearrange this equation and find x1. So x1 is equal to V1 minus Vf divided by Vg minus Vf. So V1 is equal to 0.011245 minus Vf is equal to 0.000886 meter cube per kg divided by Vg is equal to 0.02383 minus Vf is 0.000886 meter cube per kg. So unit is cancelled, and x1 is equal to 0.45. This is the solution of part number A. Now in part number 2 we have to find Q from 1 to 3. So for this, first we are finding work, because from first law of thermodynamics there is a relation between heat, work and internal energy. So first we have to find the internal energies and total internal energy and work. So we know that U1 is already calculated by us. U1 is equal to, sorry, U3 287.905 287.905 kilojoule per kg. This is basically U3. Now we can find total internal energy from this, because we know that specific internal energy is equal to total internal energy divided by mass. So this implies that U3 is equal to cross multiply mass multiplied by U3. Mass is 5 kilogram and the value of U3 is 287.905 kilojoule per kg. So total internal energy at state 3 is 5 multiplied by 287.905, which is equal to 1439.525 1439.525 kilojoule. This is kilojoule because kilogram is cancelled with kilogram. Now we are finding U1. So as we know that U1 is equal to UF plus X1 into Ug minus UF. So U1 is equal to UF is equal to 72.24 kilojoule per kg. 72.24 kilojoule per kg plus x1. X1 is equal to 0.45 and Ug is equal to 255.90 255.90 minus UF is 72.24 kilojoule per kg. So U1 is equal to, simplify this, so the value of U1 will be equal to 154.887 kilojoule per kg. 154.887 kilojoule per kg. Now we can find total internal energy as U1 is equal to total internal energy divided by mass. So this implies that total internal energy is equal to mass multiplied by specific. Mass is 5 kilogram and U1 is 154.887 kilojoule per kg. So U1 will be equal to, kilogram is cancelled with kilogram, so total internal energy at state 1 is 774.435 kilojoule. Now we are finding work done from 1 to 2 and work done from 2 to 2. Work done 2 to 3, sorry. So work done from 1 to 2, from 1 to 2 pressure is constant. Equation for work done is minus integral of P dV, which is equal to, as pressure is constant, as P1 is equal to P2 is equal to P. So we can write this as MP is constant, so MP integral of dV. Integral of dV is equal to V, and lower limit is 1 V1 and upper limit is V2. So which is equal to MP, apply lower limit and upper limit, V2 minus V1. So W from 1 to 2 is equal to MP V2 minus V1. So putting here the value of mass is 5 kilogram, pressure P1 is equal to P2, and this is equal to 1085. This is 1085.7 kilopascal. 1085.7 kilopascal. Pascal is equal to Newton per square meter. And V2 minus V1. V2 is 0.02249 minus V1 is equal to 0.011245. 0.01245 meter cube per kg. So kilogram is cancelled with kilogram. Square meter will be cancelled with square meter. So there will be 1 meter left. So W from 1 to 2. Simplify this value. So work done from 1 to 2 is equal to 61.04 kilojoule. Kilo and Newton meter is equal to joule. So W from 1 to 2 is 61.04 kilojoule. Now we know that now from first law of thermodynamics, Q minus W is equal to U2 minus U1. So Q is equal to W plus U2 minus U1. So in our case we have to find work done Q from 1 to 3. There are two processes. So heat transfer from 1 to 2 is heat transfer is equal to heat transfer from 1 to 2 plus heat transfer from 2 to 3. So apply this law here. So Q from 1 to 2, 1 to 3 is equal to W work from 1 to 2 plus U2 minus U1 and plus work done from 2 to 3 plus U3 minus U2. So this is plus U2 and this is minus U2. This will be cancelled. Work done from 2 to 3 is equal to 0 because volume is constant, V2 is equal to V3. V2 is equal to V3, volume is constant, and in constant volume process work done will be equal to 0. So Q from 1 to 3 is equal to work done from 1 to 2, our plus U3, our minus U1. So Q from 1 to 3 is equal to W from 1 to 2 is equal to 61.04 kilojoule plus U3 is equal to 1439.529 1439.529 kilojoule minus U1 is equal to 774.435 kilojoule. So heat transfer from 1 to 3 is equal to, simplify this value, so heat transfer will be equal to 726.13 kilojoule, and positive sign means that heat is supplied to this system. So this is the end of the problem, and for more problems please like and subscribe my YouTube channel and share with your friends. Thank you.